So we can actually use this information about quadratics to do an application problem. So in projectile motion, we can always model the height of an object by using a quadratic equation. And the form of the quadratic equation will always be negative 16t squared plus v naught t plus h naught, where v is initial velocity and h naught is initial height. So we're told that we've thrown a rock straight up in the air at a velocity of 50 feet per second from a roof of a building that is 100 feet tall. So this is your v naught and this is your h naught value. So our parabola, if we plug those values in, are negative 16 squared plus 50t plus 100. So now we want to know, well, when is the rock at a height of 130 feet? So that is another way of asking, for what value t does the parabola equal 130? So we can do that by finding the intersection of these two graphs. So in my calculator, I'm going to go to y equals and clear. I'm going to enter my parabola, negative 16t squared plus 50t plus 100, and then I'm going to graph the function 130. I'm going to go to my window when it's done. There we go. And let's look at this from negative 10 to 10, and we're going to zoom fit as well. Oops. So we can see the curve goes up, right down, and that 130 is way at the top. I can't really see it too well. So I can actually go into my window on the y values and see it's got y down at like negative 2000. We don't really need to go down that far. We'll take it down to like negative 500. And it's got our y max only going up to 138. So why don't we take that up to like 200 and now graph it again so we can get a little bit clearer picture here. So there's our function and there's the line going across. So this thing doesn't go much above 130. It's pretty close to the top. So what I want to do is I want to find the intersection of this graph, and it's very possible that this happens twice. So the first thing that I'm going to do is second calculate intersect, and this does not let me pick bounds, it just lets me choose curves. So it's going to pick the first function, the second function, and by default it's always going to give you the first value coming from the left. So it gives me an intersection of 0.81 seconds. But there's a second one, so I actually can't find the second one on this screen the way this picture looks. So I need to actually crop this function so that it's only going to show the second intersection. So one way I can do that, if I go to my window, since I know the first intersection happened at 0.81, I can start the graph at 1, so just to the right of that intersection, and now graph it again. So we can see the curve come down, and we can see the line come across. So the first intersection's just past this, and there's our second one. So now if I go to second calc intersect, there's the first curve, it's grabbed the second curve, and we get another point of 2.32 seconds. So this should actually make perfect sense that we got two answers, because the object started at a height of 100, it was going up, so it crossed 130 on its way up, and then crossed 130 again on its way down. So B wants to know what's the maximum height that the rock reaches, and so I'm betting it's going to be greater than 130, since we hit 130 twice. So I'm going to go back to my window and back this up just so I can make sure that I've grabbed that vertex in my picture. And it shouldn't matter, but just in case, I'm going to go in and I'm going to get rid of the line because I'm done with the line. So that way, when I ask for the maximum, the calculator doesn't get confused about which function I want it to check. So we're going to go to second, calc, maximum, and left bound, we'll say -10 to 10. And once again, the vertex, I want the entire point, but when you're doing an application problem, maximum height, we just want the y value because height is the y value here. Then it says, when does the rock reach max height? So that would be the x-coordinate of the vertex. So in this case, this is variable t, and the x-coordinate is 1.56 seconds. So now these first three problems, or parts of this problem, actually all tell the same story. The object started at 100, it crossed 130.81 seconds later, ended up going all the way up to 139 feet, then started falling. It did that at 1.56, so that was in between this moment. Then it started falling, and in around 2.32 seconds, it crossed 130 again. So then it says, when does the rock hit the ground? So this is the same thing as asking, when is height equal to 0? So if we go back into our calculator, if I find this 0, that's going to give me a negative t value. And we actually don't want a negative t value because the actual path the object took is here, right? The model or the equation gives us a complete parabola, but for this problem, we're actually only looking at it here. So if you get negative time in a question like this, we throw the answer out, but mathematically, this is why you're getting the negative time. But it was before we actually started looking at the rock. So I want to only grab the intercept to the right of 0. So I'm going to go second, calculate, 0. My left bound, I'm going to put 0. My right bound, I'm going to take it all the way out to 10. And it tells me at 4.51 seconds.